let us compute. So we are now going to work on two SVD calculations. I'll separate them out to two pieces. And the first one, very simple matrix. This character here. It's a 2 by 2. So M is 2, N is 2. We really could have made those more separate in sound, but we did not. And therefore we'll end up, when we do the SVD story over here, we're going to have U sigma V transpose. They'll all be 2 by 2s, right? So sigma in the middle here is going to be doing the work of, right, this character that's going to be doing the work of A, and the other, we can think of V transpose and U as basis transformations. There's a lot encoded in what sigma really is, but okay, good. So just going to work through this. So step one, we're going to find the eigenvectors of A transpose A, and that will give us the sigma values. Very important to remember that these are the squares of the sigma values that we'll see on the diagonalized version of A transpose A for its eigenvalues. And we'll find the orthonormal basis that the eigenvectors provide, because this is symmetric, will give us the correct basis for row space and null space. Right, so just going back into these notes. So this is the, right, it was just a few pages before. This is the big observation we made, right? So that we can make this, we can construct this factorization of A, and in doing so we figure out that A transpose A and AA transpose matter tremendously. All right, so let's get to that. So we just simply set this up. So A transpose A. All right, so we can take the transpose here, flip it around, and then we have 3, 3, minus 1, minus 1. All right, so let's multiply these things out. So there's 9 and 9, 18, minus 6. We expect it to be symmetric, right? So minus 1, minus 1, minus 1 times 3, etc. Right? So we get minus 6 again, and then we get plus 2, right? That's a plus 1, another plus 1, add them together. Just the basic matrix multiplication. Right, so we see note symmetry. If you're computing something, an A transpose A or an AA transpose, you must get a symmetric matrix. All right, so the game now is to find the eigenvalues and eigenvectors of this blob. So now solve, so this is that's the first piece. All right, so the second piece would be solve the characteristic equation. So it's A transpose A minus lambda I, set this equal to 0. So we're subtracting lambda off the main diagonal. So this is good. So it's going to be 0 is equal to this matrix. With lambdas subtract off there, there's a minus 6 still, 2 minus lambda. Okay, so determinant over 2 by 2. 2 minus lambda, minus 6 times minus 6, minus that, so there's going to be minus 36. So then we just work with this a little bit, so it looks like we have, very sneakily, right, so there's going to be a 36 minus 20 lambda plus lambda squared, minus 36. How about that? All right, so our not at all contrived example has some nice properties, so we're going to end up with lambda and then lambda minus 20. Okay, so there are two eigenvalues as expected. That gives us, and we order them by size. Pretty clear which one's number 1. Lambda 1 is 20. Lambda 2 is 0. Good. Right. And this is the square of the first one, the first singular value, and this is the square of the singular value. So we end up with sigma 1 equals the square root of 20. And sigma 2 is 0. The 0 is quite meaningful here. Very special thing. It's not. So if you like, it's not really a singular value, but I'll just put it there. So this corresponds to the null space problem, right? So this is row space and null space. This is a times x equals 0. All right, we've got a little, we'll come back to that, but we have a little more work to do. So now so this would be, let's find the eigenvalues, see what they are in terms for the eigenvector, for the singular values. All right, so I'm just going to indicate this is a thing here, that's important. And now each one, right? So n eigenvalues you have to go through and find, I mean, could be repeats, but basically now find the eigenvectors associated with them. So lambda 1 equals 20. We have to solve A transpose A minus 20 times I V equals 0. Right, this is for eigenvector 1. Fine. So this is really the problem. We've got it here, right? I'm going to put lambda equals 20 here. So we've really got minus 2, minus 18, minus 6, minus 6. We're really solving this null space problem. Yeah? And for 2 by 2s, the rows are always multiples of each other, and it's always easy to construct a solution. So let's put that in. Rows must be multiples. Of each other for 2 by 2s. Well, unless one of them is 0, 0. Because we do row reduction, we'll get zeros along the bottom row. And you can always jump here because we can flip. We can see V1 has to be at right angles to each row. So we can say, we could divide through by 2. So 3 minus 1 would work. Yep. All right, so minus 2 times 3 is minus 6, and then a plus 6 from the second part. So we can just see that. And we need we'll make it into a unit vector. A little hat on it, a little putty hat, and the length of that is 9 squared plus 1 squared, square root of that. So we're done. So that's a good little unit vector, right? So lambda 2 equals 0. Right, so now we're going to solve actually the straight up null space problem, minus 0 times the identity times V2 equals 0. Right, so that's out. Okay, good. So this one is simpler. There's nothing, we're not subtracting anything off, so there's 18, 6, minus 6, and 2. There's a minus 6 there too, right? 0, 0. Right, just taking this construction. And the same story, we just need to find we can just read it off, we can just swap them, right? We can put 6 and 18, right, and swap the signs, so we could do that, and then divide through by 6, and normalize it properly, so 1, 3, right? That's at right angles to both of these rows. And so we see, as promised, right? It's a symmetric, A transpose A is symmetric, as promised. V1 is perpendicular to V2. Right? Pretty good. Okay, so that's a good thing. So we have those two pieces. This has given us a lot. Now we've got the V matrix. So let's make that. Okay, so far we can do this. So far we have V. We just stack them up. We always use V transpose back over here, right? V transpose appears here, but V itself is just the normal story for an eigenvector matrix. There's a 1 over root 10 we can bring out the front, and then we have 3 minus 1 and 1 and 3. There's that one, and we have sigma. We can already write this down. It's the square root of 20, not 20, the square root of 20. Okay, and then diagonals are here, and then a 0 here as well. So this is a rank 1 matrix. Right. R equals 1 rank. Good. One singular value. That's right. Okay, so we need U. This is the way we'll do it in general. So we need U now as well. So two ways to do this. We could either solve, and this might be an exercise for you, either solve for eigenthings of AA transpose. So we're guaranteed to get eigenvalues square 20 and 0. So we should get lambda 1 equals 20 along with some mu1, and lambda 2 equals 0 along with some mu2. So this is one way to do it. So better is to use this, the connection between, right, that A sends V to U, VI to UI, multiplying by. So use this connection. This is the basic story we're trying to figure out. Equals sigma I UI. See, we have to be a little bit careful with the left null space, but we'll get to that. Okay, so just switching this around means that UI equals 1 over sigma I A times VI. Right, this is, I'll put up here the rank 1, so sigma 1 equals square root of 20. That's it, it's just one singular value. So this is a better plan, we're going to use this. Okay. So we'll just, right, so U1 is 1 over the square root of 20. Right, this is 1 over sigma 1, A times, and it was 1 over root 10, 3 minus 1. Okay, so these things are, this is sigma 1, this beast here with the square root, this beast here is V1 hat. Right, so we just multiply this out. 1 over, we can pull out the 1 over root 20. Let's just leave them as pieces like this to start with. We'll do some things in a minute. So this is, yeah, so it's 3 minus 1 minus 1. It's worthwhile if you want to do the AA transpose. You should, that's a nice little side exercise. And then we have 3 minus 1 here. All right, good. So this is 1 over root 20, 1 over root 10. I know I don't really need to do that. And then this is 9 plus 1, so there's a 10 here and another 10 here. Interesting. How am I doing for space? All right, good. Then this is really 1 over root 2, and we can take a root 10 and connect it with the other root 10. So now we have 10, 10. Like this, everything divides through, and we end up with 1 over root 2, and then 1, 1, which is a very nice kind of unit vector. Good, 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 good. Now we can't use this, right? So for U2, we can't, right? There's no sigma 2. We just need a vector orthogonal to U1. Right. Which we can just do by inspection. Because of our gained wisdom, we can just say U2 is equal to anything. Well, there are two choices. and this is pretty good, right? So this is rotating around in this direction. So let's draw what those two would be, just a small graph, and then we'll have a bigger one piece, right? So this is U1 would look like this, and U2 would be here, right? So that has the nice kind of like XY or X1, X2 rotation. All right, so we can put everything together. Yep, we can put everything together, and then we'll draw a picture of how this thing is working. So A equals 3 minus 1 minus 1 is now going to be equal to this thing. So the U matrix is first, 1, 1, minus 1, 1. And then we have our sigma, which is the square root of 20. It's the only thing that's really there. And then we have 1 over root 10 at the front, 3 minus 1, 1, 3. But it's a transpose, so I just need to swap these pieces. Right. Okay, so let's indicate what they are properly. Right, so this is U. Sigma, so you have to, whoops, that one fell apart. Sigma, and this is V transpose. Good. So the story is that this is a better way to view A, right? So this is to represent A. Right. A is a tiny little 2 by 2 matrix, but this product of 3 matrices is better. All right, so what is going on? So let's make a clear picture. Let me get rid of this. Okay, so we're yeah. Make that a bit bigger. Okay, so we've got some axis over here. Square root of 20, what is that? It's about 4 and a bit. So this is where the x's live, right? So this is x space over here. This is y space over here. This is really Rn. I don't like that guy. That's not good. So there's an Rn over here. This is Rm. We're talking about A times X. How does this thing work? So we have these V's, right? So where are our V's? So there was this one, which is 1. So it's 3 minus 1. Right, so let's call this. Okay, what I'm going to do is put them on a unit circle. If I can draw a unit circle. Nope. I know I can use that thing, but. All right, so let's call this 1. These is x. This is x1, x2. This is y1, y2. Okay, so now we're going to have this character here, and then this one here. So this is v1 equals 1 over root 10, and then it was 3 minus 1. Right, so this is, it's normalized, of course, so it's on the unit circle. So this is a unit circle. And then this is v2, which is 1 over root 10. It's at right angles. And it's 1, 3. Okay. So it turns out that this is null space. This is the null space of A. over here, this is the column space of A. Sorry, the column space of A transpose, which is row space. So row space, null space. And what do we see? So we see that A maps V1 to U1 and multiplies by a factor of square root of 20. Okay. So we take this unit circle, we send it over here. And in fact, the only thing that really works is that the only thing that goes anywhere is this character, right? So a line is mapped to a line. Let's get that right. I'm going to draw it over here. So over here we have, it's a simpler set of axes. So there's I'm not going to draw as big as that. I'm going to get this wrong in size, I suppose, but this is a little unit circle. Okay. Little unit circle there. So we've got the U's live over here. So let me put that here. This is the V's. And the U's are over here. Okay. So this is going to be U1, right, which is 1 over root 2, 1, 1. And then this is U2 over here, which is 1 over root 2, minus 1, 1. And let's add the rest of the subspaces. These are, of course, at right angles to each other. And this is, okay, good. So this line here is being mapped to this line. And in fact, let's draw a mapping. I'm going to draw this, I suppose. So this is A times V1 equals the square root of 20 times U1. And this is mapping row space to column space. So let's, this is column space, this thing, column space. Just going to do it thoughtfully, and this is left null space. We cannot make this, right? So this is the unbuildable reality. Inaccessible. The only two things is the highlighted blue goes to highlighted blue, and there's a stretching factor of the square root of 20. So really, so now we see A sends, so we see A sends the column space of A, transpose, row space, to column space with a stretching factor, right? Just takes this whole thing, puts it up over here with a stretch factor of the square root of 20. Now, the rotations and so on are all encoded in the basis transformations. But this is a line in 2 dimensions gets sent to another line in 2 dimensions. In general, a matrix will send an r-dimensional subspace to an r-dimensional subspace, and you can go back and forth between them. And whatever's left over is left null space and right null space. So A is invertible. A's action between CA and transpose and CA, so row space and column space, is invertible. It's just some good things to know. Okay, so there's a lot of good stuff here, and of course it's only a 2x2 example. The next one will have a full column space and a full row space. Again, 2x2s, but let me jump forward. this is the picture we're getting to. And I feel like this should have some highlighting. Yeah, I made a lot more of these pictures, but I haven't put them into these notes as much as I should have. But this is our big picture as we've had before. Right, so in general, we're thinking about AX equals B. We may not be able to do that, right? So all we can get to quite often is we project B onto column space, and then we solve that problem, and that's the normal equation. So the normal equation in general has two pieces. It has a null space vector, which gets sent to 0, and if null space is not 0, then there are infinitely many to choose from there, and it has a row vector that gets sent to P. We cannot make B if it's got some part that lives in left null space. So this is what we've had before, but now we have this extra story that there is a beautiful basis for all of these subspaces. Orthonormal, and the V's, V1 gets mapped to U1, V2 gets mapped to U2, and so on, right? And there's a stretching here. The orientations encode all sorts of rotations and flips and all those pieces, but the sigma ones do the give us the stretching, if you like, right? And so they're all positive numbers. So that's a good thing to add here. Sigma I is greater than 0. All right. Okay, so hopefully that is a good example to kind of think about here. You should be able to do this. And SVD, very powerful, used a lot. But this is just a straight up calculation example. All right.